discussion of distribution of speeds among the molecules of a sample of a gas. We have already noted that all the molecules in a gas are moving but not with the same speed. Hence, they do not have the same kinetic energy. At a given instant, a few molecules are moving very quickly. Most are moving at close to the average speed, and a few may be in the process of colliding with the surface, that is the wall of the vessel, with a minimum speed. If we could watch an individual molecule, we would find that its speed would continually change as it collides and exchanges energy with other molecules. Look at the following figure, in which graph has been plotted between number of molecules of oxygen gas versus their speed. Then, higher is the point on the curve, greater the number of molecules going at that speed. Thus, some molecules are moving very quickly, they have higher kinetic energy, and some are moving slowly, that is, they have low kinetic energy. There is, however, a most common speed represented by the maximum of the curve. This is called most probable speed alpha. For oxygen gas at 25 degrees Celsius, for example, it is about 400 meters per second, and most of the molecules are within the range 200 meters per second to 700 meters per second. It is further clear from the same figure that as temperature is increased, the most common speed alpha increases, as well as the number of molecules possessing higher speeds also increases. Of course, the areas under the two curves representing the two samples of the same gas at two different temperatures are same, because the total number of molecules is same in both the samples. Now, look at the following figure, which represents curves for different gases at the same temperature. Since kinetic energy is equal to half mv square, hence larger the mass, smaller must be the speed. The above figure illustrates this. The peak in the curve for the heaviest molecule, oxygen, occurs at a much lower speed than the lightest helium. It is very important to note for both the above figures that since curves are not symmetric around their maxima, the average speed of each type of molecule is a little faster than the most probable speed alpha given by the peak. This explains why alpha cannot be used in kinetic gas equation. In fact, Maxwell, on the basis of theory of probability and using Boltzmann distribution of molecules within various energy levels, gave the following relation, that is 1 upon n dn by dc is equal to 4 pi into within bracket m upon 2 pi rt raised to power 3 by 2 into e to the power minus mc square upon 2 rt into c square. Mark it as number 1 equation, where n is equal to total number of molecules in a gas sample of molecular weight m and at temperature T Kelvin. dN means number of molecules which possess speeds between C and C plus dC. The left hand side of the above equation, that is 1 upon n dN by dC, represents the fraction of molecules possessing speed between C and C plus dC. If a graph be plotted between this fraction of molecules versus speed of molecules at various temperatures, the curves obtained are similar to that drawn earlier for oxygen gas.